He was working as an engineering consultant at PELS Kochi till 2018 and has been in the field for more than 1.5 decades. He has participated in hundreds of academic and non-academic projects and researches in communication systems, digital image processing, power electronics, power system, and embedded system. He is especially practicing MATLAB-based hardware implementation of communication and control system using embedded coder support package in TMS320 and also in other microcontroller boards. His main area of interest lies in power electronics, electric vehicles, and renewable energy. With all privilege, we welcome you to the workshop, sir. Over to you, sir, please.
Thank you. Good evening, all of you. And I thank you all of you for arranging such a wonderful program. I think it is the best chance for me and all of us to share gathered information, collected information to all of you. I think we can start with a slide. I'll share a slide to you. This is our topic, microcontroller selection and coding for Polytronics and drive projects. I have suggested this topic because I have found a lot of problems when implementing some research and products. Hello, sorry, there is some interruption. Then I have suggested this topic just because a lot of problems are facing when implementing Polytronics drive projects and research topics, and some hardware implementation, industrial type hardware implementation. So we are using different microcontrollers, just like TMS320, C2000, and so on, for our research projects and our commercial products. And this agenda is to discuss role of microcontroller in Polytronics and drives application. That means we have to identify the need of controller in Polytronics and drives applications. Because we are doing some experiments, products, and researches on drives as well as Polytronics. In that case, we will stuck in some implementation side. Maybe some in hardware implementation, just like a converter implementation, inverter implementation, and so on. And some other cases, there will be some stuck in control loop implementation side. Nowadays, most of the control loop or algorithm implementation is going on by microcontrollers or DSP process or FPGA. And we'll discuss more about the factors affecting microcontroller selection. There will be a lot of facts. I could see that when selecting a microcontroller for an application, they will choose roughly a controller based on their experience or based on some opinion from others. In most of applications, we can see that it is not suited, that microcontroller is not suited for that application. Maybe some Arduino may be selected, or some other devices. In some drive applications, some used Raspberry Pi itself. I think that is not suited for a drive application or Polytronics application. And we'll discuss more about ARM, ARM, TA microcontrollers and Arduino. And the features of TA and STM32 microcontrollers. And we'll discuss about coding techniques and Simulink-based code generation. This is a basic agenda from me. Let me just discuss about Polytronic circuits. We know that there is a lot of Polytronic circuits, just like DCDC converters. In DCDC converters, there will be switching circuits, MOSFETs, inductors, capacitors, and so on. The role of microcontroller is when it has to be controlled, just like an MPPT, or just like programmable power supply, just like a grid interactive inverter or something. In that case, there should be a programmed logic, or there should be a closed loop control system. In that case, we should have a controller, programmable thing. In here, I am proposing a microcontroller or FPGA in that case. Next is inverters. We know inverters, there is different types of inverters, three-phase, single-phase, sinusoidal, non-sinusoidal inverters are there. In most of inverters, there will be switches. Say, in case of single-phase inverter, there will be 4 switches. In case of three-phase inverter, there will be 6 switches. And multi-phase or multi-level inverters, there will be much more switches. In that case, there is only on and off state for each switch. That means, for instance, some switch will be on, for instance, some switch will be off, depending on our output waveform and current, depending on the application. In that case, there should be some digital logic. That means in both these applications, in DC-DC converters and inverters, there is on and off state for switches. In that case, we can simply adapt digital control system based on microcontrollers or FPGA for controlling these things very easily, because these things are working in on and off mode only. And it need analog part. In that case, we can use analog to digital converters to interact with analog world. And there'll be other applications just like motor drive. In motor drive, we can see that there is a lot of motor drives available in market. In case of EV, or in case of solar air conditioners, in case of a normal inverter drive air conditioners, in case of normal BLDC fan, all these are working in motor drive application. In recent years, most of the motors are driven by motor drive only. Without drive, there will be less number of motors are using. All the applications are converting to motor drive based applications. And there are battery chargers, different types of chargers, solar chargers, and nowadays electric vehicles are coming. There is a lot of opportunities in charger field. We have also their project proposals for EV chargers. And in case of renewable energy, there is a lot of programmed applications. So we are discussing about microcontroller programming. So there are a lot of microcontroller-based programming application in renewable energy also. And energy management. When there is energy to be managed, in some cases, energy should be stored or energy should be conserved. In that case, energy management can also be determined by the microcontroller. Basic requirements in Polytronic side is PWM generation. Different types of PWM generation are there. Pulse width modulation, and there are pulse frequency modulation, and different pulse position modulation techniques are used in different applications. And sine PWM is widely used in different motor drive and inverter applications. And control loops. We are studying in control system. That's a separate subject. When we try to implement the control system in our Polytronics or drive application, there will be a control loop. We can see that there will be mathematical equations, proportional, integral controls that should be implemented inside the microcontroller to achieve the control output. And there will be a lot of algorithms, just like MPPT algorithms, fuzzy logic, and different algorithms that should be converted into real application using these microcontrollers. And the real-time operations. All these we are discussing about real-time operation. That means everything should be done in time. Here we have a DC-DC converter example. That's a simple example to describe the role of microcontroller. Here we have a PV array and a DC converter and flow. It's the simplest form of Polytronic application with MPPT. Here we can see that there is a SEPI converter that can convert PV voltage and current to the load using a PWM technique. Here we have an algorithm, MPPT algorithm, that will read voltage and current from PV side, and it will determine whether which frequency or which pulse width should be applied to the switch, and based on that it will track to the MPP point. There's different algorithms, just like P and O, incremental conductance, fuzzy logic, and different accuracy algorithms and complexity algorithms are available for tracking MPP. We can implement these algorithms into the microcontroller. I'm just discussing about the features required to implement these things. That means here in this application, we can see that there's a switch that is connected to the microcontroller through a driver circuit. That means switch can be on and off. That can be called as PWM, pulse width modulated signal. That PWM should be inside the microcontroller, and controller can increase or decrease the pulse width based on internal operation, and that internal operation will be dependent on the voltage and current reading from the PV array. There should be analog to digital converter. Here we should have PWM and analog to digital converter and MPP algorithm. We can choose a microcontroller with minimum capabilities for generating PWM within our frequency range, and there should be ADC that should be enough accurate to measure voltage and current from PV side, and there should be an MPPT algorithm. We can see that most of the MPP algorithm will take a very less load to the microcontroller. In this application, we can go for a small capacity microcontroller, just Arduino, just like PIC or other STM controllers. Here we have another application, solar inverter. We are discussing only the need of microcontroller. We can see that there is a PV array and a converter, DCDC converter, and inverter and a grid. Here, similar example from previous. There is MPP algorithm and PWM generator and a DC converter that's fed into a DC bus. From that point, there is an inverter. In that case, we can see that there is a lot of features needed. That because grid is continuously oscillating at 50 Hertz or 60 Hertz. In that case, we have to run along with the grid. That means every instant we should follow current and voltage of the grid. That means it should be synchronized. That synchronization is done by PLL, phase lock loop. That phase lock loop is purely a software or firmware algorithm that should be implemented inside the microcontroller. And there will be PWM generator and feedback system, control loop system. There will be current control scheme, and there will be bus voltage control scheme. All schemes are should be implemented inside the microcontroller using different mathematical techniques. So basic structure. This will inject a sinusoidal current to the grid based on the power available from the PV. In this case, we will need a microcontroller that should be more complex, more featured than previous application. That means it is more complex than normal MPPT application. Here, it should work along with the grid, as I said. That means it should travel very fast along with the grid. That means in this case, we should need a faster microcontroller. That means normal 8-bit microcontroller will not be enough for these applications. In such application, most of the products are using 32-bit microcontrollers. We'll discuss about high computing capacity microcontrollers and its features in later sessions. And here this three-phase inverter, exactly similar to single phase. The only difference is in single phase, there will be a current injection algorithm directly. That means that can be direct injection or other transformed mode. In three-phase inverter, all these things are converted into DC equivalent. That means there will be Park and Clark transform. to convert three-phase component into equivalent DC component, DC values. There will be a control loop inside the microcontroller. It will generate output parameters. Based on that, it will generate a PWM that will fed into 6 switches. That is a three-phase PWM inverter. That 6 switches will generate proper sinusoidal current to the grid. Exactly similar to single phase, but there will be three-phase current injection system that will be controlled inside the microcontroller using a different algorithm. I am just discussing about this just because here there will be different transformation and the control algorithm used rather than direct control in single phase. Here there will be different transforms. In different transforms, we will need different calculations, just like a trigonometry calculation or something. In that case, we should have sufficient algorithm to create that solution. In this case also, there will be different controllers and solutions that we can use. We'll discuss about it. This is about a motor drive. It's a motor drive application block diagram. The simple block diagram. There will be an inverter, power converter inverter, and a controller, and there will be sensors. In this application, exactly similar to previous thing, there will be a three-phase inverter. The electrical source will be DC in most case application. DC will be fed into the motor using inverters. Basically, it is three-phase inverters or multi-phase inverters or multi-level inverters, depends. There will be a controller that will generate proper pulses for the inverter, and that will be based on sensors. There will be different algorithms, just like direct torque control, field-oriented control, and different control algorithms are available. That algorithm should be implemented inside the microcontroller. For different types of motor applications, just like induction motor and PMSM, BLDC, most of the application block diagram will be like this. Only difference will be the control algorithm. Based on control algorithm, we should have to select proper microcontroller for getting better performance. Here, a schematic for motor drive application. We can see that there is a DC source and 6 switches and a load. There is an equivalent. Here we can see that load is BLDC motor, and there is equivalent resistors, inductors are shown in the picture. And in this case, we have to control 6 switches based on motor position. There will be sensors to the microcontroller. There will be current control scheme should be implemented. Maybe park and clock transforms that should be implemented inside the microcontroller. There will be control loop, PI controllers or something. There can be, there can be multi-phase PWM generator, maybe 3-phase or 6 or 5-phase or something. All these things should be implemented inside the microcontroller. So when we choose a microcontroller, it should have the capability to drive the system in sufficient speed. We will discuss about the performance parameters that affecting microcontroller selection based on our application. Here this is an example of a motor controller. This is a packed controller for EV application. This is EV motor controller with input and outputs. All are packed. There will be communication system. This is shown for just for an example. This is used in EV application. It's a motor controller block diagram, basic motor controller block diagram. There can be velocity reference, that means speed reference, and that will be converted into current reference. There will be current controller. It will control current using different transforms, spark and clock and inverse transforms, and there will be space vector PWM that can be all these things. We can see that all things shown in blue color that should be implemented using microcontroller. That means velocity controller, that may be a PI controller, current controller may be PI controller or hysteresis current controller or something. All these things should be implemented using digital control system, maybe a microcontroller or FPGA or something. There should be PWM generators that is connected, that can be connected to the three-phase inverter, and we'll discuss about the three-phase PWM. Then there will be control algorithm and different controllers. We'll discuss about the controllers. There is different controllers that is tuned for motor control application are available in the market. For driving three-phase inverter, there should be 6 pulses, and 6 pulses should be synchronized. That means all 6 pulses should be generated from one PWM module. That can be called as motor control PWM. There is there was some mistakes when selecting controller. Some select Arduino or some controllers for application that is not suited for motor drive. That means there is no motor control PWM inside Arduino. But we can see that someone are working on Arduino for motor control application. That means there will be less performance in that motor drive. And this is a EV charger picture. I'm just discussing about this one because we have a project that in a discussion stage. That's a high power, that is fast, easy DC-DC charger. Here we have 2 type of charger. One is onboard charger. That means there will be a charger inside the vehicle. That means when we can plug the AC supply to the vehicle, there will be DC-DC converters, AC-DC converters inside the vehicle. It will charge the battery. But in this case, the power will be very less. That can be 6 kilowatt or 7 kilowatt or something. For faster charging, when they use EVs, there will be problems of vehicle getting charged. It will take time to charge. It will make several problems. So in that case, there will be public chargers, fast chargers, DC fast chargers. This is one of most revolutionary change that can come into India, because most of the vehicle are coming from imported technology, but chargers are planned to be made in India itself. So there will be a lot of opportunities in DC fast charging stations. In these fast charging stations, there is a lot of provisions, a lot of possibilities for the microcontrollers. That means there will be communication from battery module to the charging station. That means vehicle will demand the power from the charger. That means a vehicle is controlling the charge. There will be communication, just like CAN or power line communication are used. There will be communication standards, just like there is one charger type is Shadamo, that is made in Japan, and there is one type is GBT, that is made in China, and one type is CS2, that is combined chargers 2, that means that is coming from Europe. Mostly India is following European standard. So there is power line communication is used in DC fast chargers that's planned to come into India. That means there is a lot of opportunities are in DC fast chargers. There is a lot of communication should be done. That means from charger itself, it should be communicated into the cloud to make it metering. In this area, there will be a lot of microcontrollers inside vehicle and outside the vehicle. This is an application, other application that is most trending, that is battery management system. That we have a project, currently we are working on it. This is a real example of BMS, battery management system, that we are using. We can see that there is a lot of components that is used for balancing cell voltage and monitoring and controlling individual cell voltage, and that can be read into the CAN interface bus using CAN protocol or something. And all these things are automotive compliant. There is AEC Q100 standard. Every component, including diode, MOSFET, every component should meet the automotive quality. That's the only challenge here facing. Here they're using Texas Instruments microcontrollers, automotive qualified microcontrollers. We'll discuss about different series of microcontrollers. This is a basic block diagram of battery charging system. There will be battery packs, different cells will be there, and there will be measurements. Every cell voltage should be measured and should be transmitted into the CAN bus. There will be a microcontroller in between CAN bus and the measurement system. There will be analog front ends. In this case, there will be a provision for cell balancing. Every cell in application point of view, lithium cells are highly explosive. That means it should be balanced, otherwise it will explode. In that case, there should be cell balancing algorithm, cell balancing circuits. And there should be SOC estimation. SOC means state of charge. How much energy available inside the battery should be monitored. That should be calculated. That can be called as state of charge. State of charge estimation is made by using different algorithms. One is column counting, that's done by counting currents over time. And other parameters, all the parameters should be recorded inside the system and should be transmitted to the communication bus through CAN. And here there should be an automotive qualified microcontroller with CAN interface. Automotive grade microcontrollers are used in different units of vehicles, just like electronic controller unit, electronic power steering, battery management system, onboard chargers, the other inverters, motor controllers, and everything. Then we are going to microcontroller specifications. We can see that there is a lot of microcontrollers are available in the market. We can classify these microcontrollers based on word length. That means how much bit it will operate at a time. That means there are 8-bit microcontrollers, just like Arduino, 8051, PIC, and so on. There are 16-bit microcontrollers, just like DSP or so on. There are a lot of 32-bit microcontrollers are coming by this time with cost less than 8-bit microcontrollers. That's a fact we have to identify. Most of the 32-bit microcontrollers are lesser cost than older 8-bit and 16-bit microcontrollers. There are a lot of lower 8-bit and 16-bit microcontrollers are coming at lowest price also. Then clock speed. Second parameter to be considered, that is clock speed. That means when we go for buying a PC, we will check for clock speed, how much frequency it will run, 2.4 gigahertz, 2 gigahertz, 2.8 gigahertz or something. Here there are a lot of different range of frequencies are available. At lower power, low frequency microcontrollers are available, and higher frequency, that is 20 megahertz. Here there is a problem. 72 megahertz and 200 megahertz microcontrollers are we normally using. Computation capacity. That means when we apply a floating point number to the microcontroller, to the program, normally just in C program, it will take some time to compute. Suppose if it is in Arduino, when we give a fraction numbers, it will compute those parameters using floating point algorithm without having floating point unit. So it will take more time. This is the main thing people does not identify in electrical application in most cases. That means when we select a microcontroller, if our algorithm is using floating point arithmetic, we must select floating point cross. Otherwise, our application will get lag. It will not work on time. It will work without real-time feature. And when we choose a microcontroller, there will be a lot of PWM features. When we use an application for motor control, microcontroller for motor control application, there should be enough PWM channels with enough features, just like 6-channel PWM with the central aligned and different alignment features. There are a lot of PWM features available in microcontrollers. And there are other features just like ADC, PWM synchronization. In some application, current will be varying with the time. With the current waveform will be varying with a different time. In some cases, it should be synchronized with the PWM that we generate. In that case, we can synchronize ADC to the PWM. That will give a stable. That means every time when we read an analog value, it will be synchronized with the switching parameter, switching pulses. That means it will be stable. It is reading every similar interval, so it will give a stable reading. That's another feature available in controllers. Here I have arranged a comparison table based on different parameters. So first is Arduino, based on bit size. We can see that there is 8-bit microcontrollers, Arduino, PIC and AVR, and DSP is 16-bit, and TI C2000 that we used, that is 32-bit, and STM32, that is 32-bit itself. And based on floating point, Arduino does not have a floating point, and PIC, there is no floating point, and AVR also there is not a floating point, and the DSP there is no floating point. And TI controllers, there are several series of TI C2000 controllers with the floating point capability. That means when we give a fractional number, it will compute very fast in few cycles. Otherwise, it will take more cycles. In STM32 also there is floating point controllers are available inside the microcontroller. And when we consider about motor controller PWM, in Arduino there is no motor controller. It's the most important thing we have to take care. There are, as I said earlier, there are a lot of application can be seen that is implemented using Arduino, motor control applications. In my point of view, and in common point of view, it will not work properly. It will not give efficient result. And PIC also there is normal motor control PWM and AVR, and there is DSP microcontroller that has motor controller PWM, TI series microcontrollers and STM series controllers also motor control PWM. And the ADC is one of the important factor that is affecting microcontroller selection. And there is a 10-bit ADC in Arduino, and PIC and AVR, and DSP is 10-bit. TI microcontrollers 12-bit ADC. Most of the motor control application based controllers having 12-bit ADC. And about ADC PWM synchronization, that is seen only TI and the STM controllers. That's a very good feature that can be used for motor control application. And programming tool, based on programming tool, we know there is Arduino IDE and PIC, that is MPLAB, and Atmel Studio for AVR microcontrollers, and MPLAB for DSP, and TI for TI. There is Code Composer Studio, and for STM32 there is different softwares available, just like Key, System Workbench, and so on. And application based on application, Arduino and PIC and AVR, those are general purpose microcontrollers, and DSP and TI-2000 STM32 are motor control based microcontrollers. And based on performance based cost based performance, that is Arduino and PIC and AVR having poor performance versus cost, and DSP medium in TI, that is better, and based on cost, STM32 is giving better performance. Here, yes.
1 second.
Yes.
Could you please take the previous slide? So looking at
Which
the
one?
table, yeah, uh, the
Which
parameters
one?
for hello,
Yes.
the parameters for TA and STM looks almost same. Okay,
Most of the parameters look same, but in case of price, that's a main factor that is affecting in India because our price margin is very less. That means here there is some difference in cost versus performance.
okay. So I have a
Uh,
motor application. Okay, so I need a high-end processor. So how to select between TA and STM? How to?
uh, Based on cost and performance. In some cases, it will take less time to develop an application with TA, but processor cost will be higher. And in some application, when use STM32, cost will be very less, but effort will be high. That's the difference. Based on quantity, product quantity, we will choose the microcontroller.
Okay,
If
what about?
quantity,
Okay, okay.
if
So if
quantity
I have a single application, say assume it's a single application.
for single application, just like a research and development or project application, I prefer TI. And for product development application, I prefer STM. That's a difference only between STM and TA.
Okay, what about the clock frequency for STM?
Both are available in higher ranges. STM and TA both are available in 200 megahertz such range.
Okay,
Both are having in automotive section. Both are having different family of microcontrollers.
okay, okay.
There are main competitors between the. Okay, thank you.
Sir, can you tell me what about the interfacing part? Like which microcontroller having the best and easy interface with the MATLAB?
Easy interface with MATLAB that is TI. Best support is from TI, but cost is bit higher. Just like for an application, for our last application, we choose STM because it is working floating point microcontroller with a cost of less than 400 rupees per device. At the same time, TI with a floating point processor will cost more than 1,200 and 1,400 rupees. That's the difference. For higher
So
quantity, it will affect.
for the STM32, we need a separate interfacing software with MATLAB.
Both should have separate software. Just like a TI, it needs Code Composer Studio, and STM32 will need Keel software. That's IDEs. But in application side, for research application, there is an option to generate code from MATLAB itself for TI. For recently, I have started STM also in that way. Okay. Okay. Thank you. Here I have a picture of Arduino IDE. That's very common. That's for only a comparison I have chosen. Arduino work with Arduino IDE. It will generate a code and dump with AVR microcontroller inside Arduino, and this code will be transferred to the binary, and there is a bootloader inside the microcontroller. I am just listing Arduino here because we don't have much idea about the hardware side based on device in different applications. That means we cannot differentiate between separate device in Arduino programming. That means every device will be treated as same. That's the simplest thing of Arduino, but in most featured application, it will not give better effect to the application. That means if we use a higher end processor in Arduino device, just like Arduino Duo is available, that is ARM processor based. But we can see that very less feature are available in Arduino IDE, but processor is higher. That's the main fact using Arduino. Okay. Here there is a programming tool for just for listing that is DSPIC, that is MPLAB IDE that is available with a microchip website. The basic software that we can use to program DSPIC and PIC microcontrollers. I'm just skipping it. I'm not concentrating on these chips. And there is a Code Composer Studio. It's the most popular thing for TA microcontrollers. we can see that these editors are based on Eclipse based platform. Eclipse means that is an open platform. There is a lot of IDEs for Code Composer Studio or ST System Workbench, and several IDEs are coming in this platform. That means all IDEs will look same, but it is a bit tough to work in these type platforms. For ST microcontroller, there is a System Workbench platform, but we use Keel platform for easy implementation. Currently, we are using Keel for our application for STM32. Okay. Here, another feature that we have used, that's the next level. We have seen these things, just like Arduino IDE and MPLAB IDE and Code Composer Studio and Keel. Apart from these, there is one higher level. That means there is a tool that can generate code. That means here we have using a tool that can generate a code template. That means we can initialize different pins for ST microcontroller using this code generator that's known as STM Cube MX. That means we can choose a microcontroller. We can configure every pin and timers, features, and every peripheral things we can tune from this application using GUI tool. After configuring everything, it will generate a code template. That means we can write code just like we are using in Arduino IDE. That means we have to write the code working part only, not to initialize the internal features or registers or something. That means code will be very simple. In STM32 application, we are using this type code generation techniques. First, we will generate a code from STM Cube. And every change we can change in STM Cube here, and it will update in our code parallelly when we are having some changes. After generating this code, we can write simple algorithms in our program, and there is a well-structured code. It will generated from STM Cube. It's a tool. This is just for information. Only thing is to be understand that there is code generation tool instead of writing code from the scratch. In nowadays, there are a lot of microcontrollers available in the market with different higher features. So that will be very difficult to write code from scratch by looking at the data sheet or something. There are a lot of code generation tool. Here for ST, one of the code generation tool is STM Cube. Okay. And one above STM Cube, there is one more.
Excuse me, sir.
Yes.
Can you tell me the code name again? What you said you using for this microcontroller?
Tool name.
Yeah, you say like we are getting a lot of codes available in the market.
Okay.
Instead of writing the code, you say like you can take a lot of code from not from
Yes.
catches.
Yes. There are code templates. That means there will be different code templates. In that case, there will be different code templates for different applications. When we try to combine.
This section is only to know the basic kind where we get, not to learn anything newly.
For this session or this slide?
For this section, overall section, is there any implementation for learning or just to know all the things what we are know?
Yes, just to know, because this time is not enough to start the learning from 1 hour. That's the main problem.
Seriously, is you are saying the overview things for everything and you skipping the coding part, everything, and
coding part that cannot be covered in with less time. Sorry.
Okay. Yes. Excuse me. This is an introductory level only because it's a 1 hour session only.
Okay.
So there is a time limit. So it's basically this session is for we planned it for UG and PG students basically because it's an introductory level course only. Okay. So we in future we will have a detailed course also. Okay.
Okay.
Thank
Yeah,
you.
yeah, that's good. That
Okay,
sounds
thank you.
better for us.
Okay.
Thank you.
There is another tool that we are used. That's a motor control workbench, system workbench, that for generating code for STM microcontrollers. Here we are having a block-based code generation tool. That means every blocks there is different blocks. There is firmware, device management, clock management, I/O management, DAC, ADC functionality, user interface, and different sensing part, and different controls, just like temperature or something. All these can be configured using GUI blocks, and we can generate a code based on this. After generating code, we can test using its GUI-based algorithm, this GUI-based interface. After this, we can modify that code to our own application. This is a higher-end tool. Similar tool is available in TA also. There is a code generation tool available in TA also. That means chip manufacturer will help us to generate a code like this. It will generate a code with our configuration. We can configure before generating code, and that code can be converted, can be modified or customized after generation. Okay. This is the tool for evaluating motor control algorithm, mostly for PMSM applications. This is a STM system workbench, and its control screen. And there is one more thing we can discuss about Simulink-based code generation. For research and development application, we use MATLAB Simulink to simulate our algorithm or application. In that case, we can convert our Simulink-based block diagram into the program for different microcontrollers, just like TMS 320, C2000 we using to generate code from MATLAB Simulink, and we can configure PWM ADC IO lines from Simulink itself. From a single click, we can generate a code. And for Arduino and DSP has same provision. Nowadays, we are using STM32 also for this type application. Basically, we use this type for DSP and STM32 and TI-C2000. This is most effective in TI-C2000 platforms. It will reduce time. It will generate code very fast. It will reduce our implementation time, and it will reduce errors also. And some industries are also using these methods to reduce their product development time. If there is any questions, we can discuss along with this. I have to manage time. Because of that, I am going very fast.
Sir, can you suggest which microcontroller is good for the DC microgrid application at the beginner level?
For beginner level, I suggest for DC microgrid application, it will be TI series microcontrollers, because there is a lot of software support and MATLAB implementation provision for TI microcontrollers. That's the best option, I think.
Okay. Sir, can you suggest which, there are a number of TI microcontrollers which could...
Yes. For starting, I suggest TI TMS 320 That's the baseline microcontrollers without having floating point arithmetic.
Okay. Thank you, sir.
So participants, before asking, it would be good if you could introduce and then ask the question. Okay. Thank you.
Sir, I have a question. I'm studying on the final year on EP department.
Okay.
Sir, am I audible?
Yes.
Okay. Sir, when we are working on a system which have different systems and we have to connect them together, which microcontroller would be best for that?
All these applications that having different units, without having a modular approach, it is not simple. It is not better to work. That means every application, it will have separate units. That means there will be some different functions, blocks, and everything. So that's a very common thing.
Okay, sir. Okay.
Thank you.
Hello, sir.
Yes.
Hello, sir. I'm Abhinan from EC department.
Okay.
So I have a question, sir. As a fresher, we are student, so we were actually not introduced about the software.
Okay.
So to end up in this industry, do in our academics.
That's a best question. Actually, industry expecting the basics only. From academics, industry expecting basics and its application. That means when we try to interview a fresh candidate, we will not expect higher end engineering from them. We expect only basics, and from the basics they can know to the very high level. That means just connect the things you learn to the real world. That's the main fact. That's the only thing you have to do.
So to end up in a industry as a fresher, what should we learn after BTech graduation?
That means just try to connect what is happening. Just try to get information in the industry. What is happening in the industry? Then, if just like EV charger or something, or CAN communication, as it you communication based student, there's CAN communication. When you try to find a job, there will be a requirement just like a CAN or some interface topologies, Ethernet interface topology. Then you just try to interconnect the method that is similar to CAN that you already studied. Just like even you have a basic knowledge in UART, then you can just try to learn about CAN without having a basic knowledge that you study in your college. That's just like CAN, just like UART, just SPA or something, synchronous or communication. Without knowing that things, it is tough to learn. That means you just get informed about what is happening in the industry, and you just try to connect your learning to that one also. So, basic thing.
And basic C, regarding C coding would be enough, basic, right? For a BTech.
Basic C coding, normally BTech students practicing. When we try to implement our C code, there is only a slight difference in microcontroller application. So better thing is you just try to implement, simple application in our academics. That means every time we should have some experience. Okay.
Hello.
Yes.
Sir, I am Finny, third year EC student.
Sorry, you are not audible. You are not audible. Hello? You are not audible. Please, raise your voice. Hello?
Hello, is it audible now?
Now it's
Yes,
good.
yes,
Please
yes,
introduce.
please.
Okay, I am Finny, third year EC student.
Which
Yes,
college?
tell me.
Which college?
Model Engineering College, Threephase.
Okay.
I have a doubt regarding the STM32 nuclear board and the discovery board. So, for practicing CAN communication, which is better, discovery board or the nuclear board?
Both has having CAN because even there is blue pill that is already having CAN. So you can go for a discovery or a nuclear. F3 or F4, all these chips having CAN. So discovery, nuclear, both are fit for CAN communication.
Okay, thank you, sir.
Hello.
Yes.
Yes, sir. This is Panidilip. I'm a PG student. Hello. Sir,
Subject?
you.
Which college?
Hello,
Hello?
Power Electronics. Power Electronics.
Which college?
Practice Engineering College, Andhra Pradesh.
Okay.
Okay. Thank you.
Sir, you said that float point is there, no, sir, which is used for MPPT controllers also in microcontroller application.
Floating point.
Yes, sir.
I didn't hear that point. That means
Floating
which you
point in.
mentioned? Floating point.
Yes, sir, floating point you have taken, no, sir, in STM12, STM32, and SIC.
Okay,
Have
for
taken.
MPPT application, that is very slower application, because
Okay.
when we apply a change or something, perturbance or something, suppose P and O or incremental conductance, we should
sir.
wait to respond. That means there is a lot of time to compute.
Okay.
That means even if it is floating point algorithm, we can go for a non-floating point processor, because it will compute in between that time. For MPPT only application, we don't have to go for a higher capacity floating point process.
For which you need to go for lower ones only.
That means you can use non-floating point controllers, just like TI 28027. Even Arduino is able for MPPT application.
Okay. But this STM32 and SS and all, you only use it for motor applications only.
No. That means if we need higher computation, even in MPPT algorithm also, if you need higher computation accuracy, higher speed in MPPT itself, you can use STM or TI. That means for higher computation speed, we can use higher process.
Okay, because nowadays grid integrations and all are happening, no, sir, vigorously. That's
Yes,
why I'm asking.
yes, sir. That is that we have to discuss about the grid interaction also. If grid integration is there, we choose a controller that is suited for grid application. The MPPT will be a smaller part in that application. That's a fact.
Okay, sir. Thank you.
Any more questions? We are going to wind up today. If there are any more questions, we can take 1 or 2 questions maximum. Okay, so
Yes.
thank you. So any concluding remarks for today's session, Aslam? If you
Yes,
have, you can summarize.
Okay. About inQbe, actually, we are a research and development organization, and we have a support service in academics also, and we are conducting courses in embedded system, Polytronics, and drives application mostly based on MATLAB and related things. And we deliver internship, 2 internship for students, for selected students only. And we have an online store. If you need specific components, that is most commonly available in online market. So there is one online store for inQbe. You can search in Google itself. And we will also support academic projects. That means there is industrial experience for us. So we'll convert it to the academics also. So we have interaction with different institutions. That's end of my session. Thank you.